Hello and welcome to Underground Storage Tank Cathodic Protection, presented by me, Luke Pike. The presentation objectives are to explain basic theory behind cathodic protection, explain the standards and criteria that need to be met, explain the types of systems that exist, talk about basic survey equipment and measuring techniques, and then at the end show examples of impress current and galvanic reports. For my personal background, I graduated from Oregon State with a BS in Chemical Engineering in 2013 with an option in Microelectronics and Material Science. I've been surveying and repairing and installing underground storage tank cathodic protection systems since 2007. First certified as a CP2 in 2011 when NACE was still called NACE. Then I got my CP3 certification in 2014. I've also passed the NACE Coding Inspector courses 1 and 2 levels. And in my free time, I am a disc golf enthusiast. So we're going to start off with the basic theory of what causes a metal to corrode. And what causes a metal to corrode is the potential difference or the voltage that is experienced at the surface of the metal. The potential differences in a metal ore are created when a metal ore or an oxide is refined into a pure metal state. This change in composition then imparts an energy into the newly created metal lattice structure. On the lower left, we have a diagram of the Bessemer process, one of the earliest methods to industrially refine metal ore. And then on the right, we have a picture of a metal lattice structure. So this is what metal looks like up close under a microscope. It's not a pure state. It's not nice and shiny as what it may look like from the outside. Down at the granular level, this is what it actually is. So now that we've established that an ore is taken from its oxide state into a pure state, we now have multiple states of metal. And then based on thermodynamic principles, a metal will always return to the lowest energy state possible, which is that oxide. When two different concentrations of energy are allowed to transfer charges, they will try and seek out a balance between them. The higher concentration will move towards the lower concentration. This occurs spontaneously when a path for charge transfer is available. So metal corrosion can therefore be described as metal returning to its lowest energy state because it is energetically favorable to do so. Just like a cycle of running and sleeping, we get tired, we have to sleep. Once we have slept, we have more energy and we can run. So we've elevated our energy levels. Once we've ran, we return to that lower energy state and we want to sleep. So we have a cycle. The only reason that metal can ever reach the higher energy state is because we refine it. Back to the kind of that Bessemer process picture that I showed is an example of we take the oxide, low energy state, refine it, put a lot of energy into it by making it a pure metal, and then the universe will always want to tend to bring that metal back into its lowest energy state, which is the oxide. So now that we have a basic understanding of why metal has a tendency to corrode from its pure state to its ore state, and when there's multiple states of energy, we can also now talk about the different states on the surface of the metal. So imbalances of any kind will create a potential difference on the surface of the metal and cause charge transfer. So these general types of imbalances can be due to temperature, moisture content, soil resistivity, pH, ion concentration, oxygen content, the metal composition in alloys, electrolyte movement. So if you have flow of water next to a surface of a metal, and presence of sulfate reducing bacteria. So these differences in surface potential, and surfaces is bold for the reason because that's the only place where these interactions occur. They don't occur back in the bulk metal where we have the potential difference. It's right on the edges of the exposed metal. So these differences in surface potential cause a transfer of charge, coulombs, through an electrolyte, soil, gravel, and water. We must have an electrolyte present, which I'll show later on, in order for this charge transfer to occur. This charge transfer results in metal loss to the electrolyte. So the electrolyte must be present, which can be characterized by Faraday's law. I will let you read through all the variables. So now kind of the big reason why we're all here, we know metal corrodes, but how can we stop metal from corroding? The way we stop this metal from corroding is with the application of cathodic protection. When we get into some definitions, we kind of got to go through it to set some standards. Definition of cathodic protection: a technique to reduce the corrosion of a metal surface by making the entire surface the cathode of an electrochemical cell. So now we have to explain what is an electrochemical cell. An electrochemical cell consists of 4 general parts: an anode, a cathode, metallic pathway, and an electrolyte. And on the right we have a diagram of all these parts together. The metallic pathway connects the anode and the cathode. And the anode and the cathode sit in our bulk electrolyte and allow for that charge transfer. A short vocabulary note before we move on: anode is pronounced anode, not anoid. All right, so we're going to keep building on our theory that we've got going on now. So we've introduced the electrochemical cell. We know about surface reactions. We know about different energy states. We know metal corrodes. Now we can specifically start to say where the corrosion occurs and what other reactions are going on. So the oxidation reaction occurs at the surface of the anode in the electrochemical cell. A reduction reaction occurs at the surface of the cathode. And now we have the word cathode popping up. So we're getting to the point of this presentation here. So continuing on with the electrochemical cell, the anode and cathode have different potential energy levels. The imbalance presented by these energy levels causes electrons to flow from the high source to the low source. So the anode is the supplier of electrons and the cathode is the receiver of electrons. If there is no imbalance of charge, then there is no charge flow. No charge flow means oxidation of the metal is no longer occurring. Going back to our previous slide, oxidation occurs at the anode only. So oxidation, I think we're familiar with that term. We probably know it as rust or rusting. So we're trying to stop the oxidation reaction. If we can stop that, then we can stop metal loss. So here we have a larger picture of our electrochemical cell diagram showing all the components, as well as the acronym ACME, which is a great way to remember all of these components: anode, cathode, metallic pathway, and electrolyte. On the left, we have a general oxidation equation that shows a pure metal going into a ion state metal. And then on the right, we have a general reduction reaction equation showing that there's the reduction of the metal and combining with an electron. Up top, from the top of the anode to the cathode, is the direction of our flow of electrons. And for the conventional current flow for physics, current is accepted to be in the opposite direction of electron flow. So if you were to show the current flow, it would be from the cathode to the anode, or you could say the current exits the anode and travels towards the cathode. ACME is an industry standard for trying to remember the parts of the electrochemical cell. This is something that I've come up with to try and have one more way as a memory tool to remember the parts. We have the corrosion square. So just like we have the fire triangle, we can have the corrosion square because we have 4 parts or elements of our electrochemical cell. And just like with the fire triangle, if you remove one of these 4 parts, you shut down the electrochemical cell. All parts must be present in order for the electrochemical cell to be active. Or you can also say for corrosion, for that oxidation reaction at the anode to be active. Going to bring it back to the definition of cathodic protection, now that we've kind of explained more of the terms: a technique to reduce the corrosion of a metal surface by making the entire surface the cathode of an electrochemical cell. So now we know what an electrochemical cell is, and we've seen what a cathode is. So that's where the current is traveling towards the surface of the cathode. We have a reduction reaction occurring at the cathode. We have our controlled oxidation reaction occurring at our anode. We have the metallic pathway allowing for that electron, the electrons to transfer in between. We have the bulk electrolyte, which allows for that charge of transfer to occur. Now I know people learn in different ways, so this is my attempt at a visual representation of trying to get the point across one more time of showing the differences in potentials. So on the left we get back to our grain structure of actual metal. So that's what actual metal looks like. And now if we can theorize, just kind of in our heads, on the right side is a topographical model of rivers and valleys in a mountainous area. So if we just think of the elevation changes as difference in energy levels, so the high points being the mountains, the low points being the river valleys, we can see that there is a flow, and then the water itself is actually a good representation of the movement in between all of the elevation points, that we can conceptualize on a single piece of metal. There are many cathodes and anodes that are allowing charge transfer to occur because of the inherent grain structure present in metal. If you can look on the left, yeah, that's the flat, but on the right, if you were just to look at it almost as a bar graph of potential energy levels, that's really what's kind of occurring on the surface of the metal. So staying with our visual learning model for looking at the different energy states, the current flow on a metal surface without CP applied could be analogous to a river rapid, where we have a high source above the rapids and then the low source underneath the rapids. And right in between, we have that charge transfer, the water transfer, and that's where we're going to get our corrosion. But on the right, if we have current flow on a metal with cathodic protection applied, this is essentially what the water would look like. There would be a placid lake. There would be no flow because there's no oxidation. There's nowhere for the charge transfer to go. So now I want to talk about some different types of corrosion just to give you an idea of the different possible forms of attack that can occur on metal. So for different types, we have uniform, localized, galvanic, hydrogen embrittlement, selective leaching, intergranular, stress corrosion cracking, microbial, and erosion. For uniform corrosion, it's kind of self-explanatory. It occurs evenly over the entire surface of a metal. This is the least problematic source of corrosion because corrosion current is evenly distributed. For localized corrosion, this is where we begin to get into problematic forms of corrosion that can cause catastrophic failures or very sudden failures on systems. And they're usually due to a difference in oxygen concentration in the metal. So for the crevice, the area with a lower amount of available oxygen will become the anode, and the exposed area next to that covered area, part will become the cathode. So this is typical in a bolt washer flange area where you have one part pushed flush up against the metal, so your low oxygen concentration area that can maybe receive a bit of moisture. Maybe it's not perfect underneath that, or maybe there's some dirt that gets stuck underneath it while parts being put together. So then if you can think of like oxygen is a great insulator, it doesn't allow electricity to flow readily through it. If you were to have a 100% oxygen or just air environment, it'd be very difficult for current to flow through that. So just visually you can think of that. And then if you were to have 0%, it's just on the other end, then that would be much easier for current to flow through an environment like that, because if we're just purely considering oxygen as an insulator, well, really air, then you would have a much easier path for the electrical current to flow. And wherever we have current flowing from a source, that's where we get oxidation. Now that's what we're trying to stop. For pitting, you have a local spot in the metal where a pocket of corrosion, so usually an imperfection in the grain boundaries will form, or it could be damaged, or it could be a holiday or something. Then it works downward towards the metal. The corrosion product will build up and reduce the available oxygen and creates an anodic area. So at the bottom of the pocket, you reduce your oxygen supply. Then over time, it actually deepens because that reaction will keep progressing as long as there's a difference in the oxygen level. Galvanic corrosion is more of a general form of corrosion, but it occurs when two dissimilar metals are brought into contact with one another. The metals touching is automatically our metallic pathway. The two different metals are our anode and our cathode, so we still need an electrolyte present in order for the charge transfer to occur. But if in, say, example, an old piece of steel is connected to a new piece of steel, then buried or submerged, the new steel will be anodic to the older piece of steel, so it will corrode first, and it will corrode at an even greater rate before the old piece was removed. Because if we think about the potential difference, that those two old pieces of steel that were in place had been in the same piece of ground for the same amount of time, so their voltage levels were relatively similar. But now you've brought in a brand new piece of steel from the factory that has the highest level of potential energy it's ever going to have, next to a lower piece of energy of steel that it has had time to release some of its energy from its lattice structure. So now that you've brought those two in contact with one another, you've created essentially the battery. You've created a greater voltage difference than was present before. So you'll actually have a failure again, probably in a fairly short amount of time. Okay, hydrogen embrittlement corrosion. This occurs when polarized potentials reach the hydrogen evolution line of a pore bay diagram. So meaning that you have reached a level of voltage that now there is a chemical reaction at the surface where you are producing hydrogen right on that metal. And this hydrogen will force itself into the lattice structure of the metal, causing an embrittlement effect. And for steel, this generally occurs at polarized potentials greater than negative 1200 millivolts relative to a copper sulfate electrode. Excessive polarized potentials with impressed current systems should therefore be avoided, and more is not always better for your levels of CP. And getting a little ahead of myself, but we'll get those terms explained here soon. All right, selective leaching corrosion. This occurs when one metal corrodes out of the lattice structure of a metal in an alloy. So two or more metals that creates an alloy. First example, cast iron pipe consists of iron and carbon. The iron will corrode first since the carbon, which is graphite, is cathodic relative to the iron. This leaves behind a very brittle structure that looks intact but is no longer structurally sound, also known as graphitic corrosion. And example 2, zinc and copper are combined to form brass. So the zinc will corrode out first since it is anodic relative to the copper. Intergranular corrosion. We got our picture of our grain boundaries back. So this occurs obviously at the grain boundaries of metal. And then during the refining process, as metal cools, grains begin to form as it transitions from a liquid to a solid. These grains form at different rates and can have different potential energies as a result. Stress corrosion cracking typically occurs in metals that are under a tensile or pulling load, causing a non-plastic deformation of the metal. Areas that are under stress will have more energy available in their lattice structure. An area that has more energy available to it will become anodic and corrode at a greater rate. High-strength metals are most susceptible to this kind of attack, and so the failures are sudden and catastrophic given the nature of their loading. So if you have a high-strength metal, you probably have a requirement that it's under a load already. So actually when you forge the alloy to be high strength, you give it this natural weak point. And unfortunately, when it does fail, it fails suddenly. Microbial corrosion, or MIC, is usually the result of sulfate-reducing bacteria, SRB, being present in the electrolyte at the surface of the metal. The bacteria modify the pH of the electrolyte through consumption of molecular hydrogen. And studies have shown, though, that a polarized potential of negative 950 millivolts CSE can prevent metal damage due to MIC. Usually negative 850 is the standard to prevent metal loss for steel. With erosion corrosion, you have metals that rely on a passive layer that protect themselves from corrosion, but in the process, you have a medium that flows over this metal and that passive layer is removed. a corrosion cell is allowed to continue instead of being slowed. So usually this passivation acts as a natural coating for the metal. A great example is aluminum, which has an aluminum oxide coating that's generated over time. It will appear as a white powder on the pipe. And stainless steel exhibits this as well. So now we get to more of the technical point on who's figured out how cathodic protection works and who are the people that tell us if we have enough CP. So if you've worked in industry for a while with cathodic protection systems, you've more than likely heard the name NACE. NACE has now switched to AMP though, Association for Material Performance and Protection. They've merged with SSPC. I'll talk about that a little short bit a little later on. But they're the main people that give out the majority of the standards on how to define cathodic protection requirements. For this presentation specifically, the EPA does give out rules for USTs. The EPA does kind of mirror what NACE requires, since NACE is kind of the foremost expert on cathodic protection. STI has their own regulations for their Type 3 USTs. ASTM has some standards, and ISO also has standards as well. So we've talked about theory. Now let's get into the specifics of how do we define if a system has adequate cathodic protection. If you've worked in industry for a while, you've probably seen this standard. External corrosion control of underground storage tank systems by cathodic protection. This was developed by NACE International in 1985. It's gone through a few upgrades since then, and I was talking about in the previous slide that NACE has merged with the Society for Protective Coatings. They are now called AMP. And underneath is a screenshot. If you see the standard, that's what it'll look like. If you keep reading, you'll get to section 5 of that standard, and it covers the criteria for cathodic protection, which we have 3. So we have the -50 on criteria, -50, 850 instant off, and the 100 millivolt shift. So we'll start off with the first one listed, the -850 on criteria. A negative cathodic potential of at least 850 millivolts with the CP applied. This potential is measured with respect to a saturated copper-copper sulfate reference electrode contacting the electrolyte. Voltage drops other than those across the structure to electrolyte boundary must be considered for valid interpretation of this voltage measurement. The then -850 on criteria is probably the simplest evaluation method, as there's really nothing to modify, nothing to change. It generally applies to Type 3 USTs. This is because the anodes are welded onto the bottom of the tanks, so the CP current cannot be interrupted, so the only interpretation for the protection of these systems can be taken as the -850 on. And in that paragraph, we have the line, voltage drops other than those across the structure to electrolyte surface boundary. So the voltage drop can also be called the IR drop. As I just mentioned, IR drop is voltage drop. So IR drop is considered an error in accounting for polarization measurements. So it gets its name from the application of Ohm's law, V equals IR. You do the math, therefore voltage drop is IR drop. And when the CP current is applied, the electrolyte adds essentially a false reading that is not a true measurement of polarization. By placing the reference cell as close as possible to the surface's structure of the surface, the IR drop can be minimized to a negligible amount. So that was -850 on, and this one is probably the most common that inspectors and anybody around gas stations will see is a negative polarized potential of at least 850 millivolts relative to a saturated copper-copper sulfate reference electrode. Pretty short, pretty sweet. Let's see else what it says. So the -850 millivolt instant off criteria, this is going to be used for impressed current systems. So it can be applied to galvanic systems if a tank has been retrofitted with new anodes, and if the anode connection is made at the top of the tank, you can disconnect the anodes and get an instant off reading. The polarized potential is recorded the instant that the CP current source is turned off, hence the name instant off. So we talked about the voltage drop being a ghost reading. So if we interrupt the CP current, we eliminate IR drop. So on potentials should also be reported for this method if the electrolyte is homogeneous, though, and the distance between the structure and surface is constant. The IR drops can be assumed to be constant, and an instant off value can be calculated without interrupting the CP current. So if you have a historically known electrolyte above an area, this is more applied for water systems because water is fairly homogeneous. If you know, if I'm taking a measurement 3 foot above a structure for 100 linear feet, say, I don't have to necessarily interrupt that rectifier for every single measurement. I can assume after I do it once or twice that I know what my IR drop will be, so that's calculated. It's basically a calibrated measurement. But for soil systems, it would be more recommended to take the instant off instead of relying on a calibrated IR drop. And this is what an instant off measurement looks like when practically applied out in the field. We have the on reading at the bottom. We have the moment that the CP current is interrupted. Then here is our true level of polarization. So we want this value right here, the moment that the CP current is interrupted. Usually I'll run about 10 seconds on, 1.5 seconds off to make sure that I get enough of a resolution on my meter. So I use a Fluke 289. It can capture the waveform. This was 3 cycles of measurement. 0, it's about 30 seconds. And with the Fluke 289, you can then zoom in on each individual waveform. So this is that same measurement. We're just now zoomed in on one of those plateaus. So we have our larger negative value here, and then when we go off, we shift more in an electropositive. So this reading was negative 709 millivolts, or negative 0.709 volts. So for me, the interpretation where it becomes flat, that's our instant off value. That's where then it's flat, CP current's been interrupted fully. You can have a capacitance effect with the pipe where there is a small amount, like a double layer capacitance of charge that's residual. So you do want to make sure that you do hold it off long enough to get that true measurement value. And on to the third criteria, the 100 millivolt shift. So a minimum of 100 millivolts of cathodic polarization between the structure's surface and a stable reference electrode contacting the electrolyte. The formation or decay of polarization can be measured to satisfy this criterion. So the 100 millivolt shift is determined by taking the difference from a depolarized potential, so no cathodic protection applied, and the instant off value. So formation or decay polarization can be used as the depolarized value. An initial instant off value is recorded, then the anodes are disconnected. The potential then decays from this instant off value, goes down, or shifts electropositive typically. If the resulting measured off potential falls more than 100 millivolts, so we can have values much greater than 100 millivolts from the instant off reading, then this criteria has been met. So the time needed to meet this criteria will vary per structure. If there's not enough CP polarizing the surface, then we will not meet this 100 millivolt shift criteria. Typically, I'll apply this for systems that are at end of life, where you do not have a full availability of current to meet that negative 850. It's like in the previous slide where we saw a negative 709 millivolts. You may see negative 709 and the tank depolarized value may be at negative 500. So then we'd still be at 200 millivolts difference, and we'd still be able to meet that criteria. So decay polarization is one way to evaluate criteria, but there is also formation polarization that can be used. So say if you show up to a site and the rectifier is found off upon arrival, it can be determined that the unit's been off for more than a few hours. Usually in this case it'll be a few days since you got the call to come out and look at the unit. The depolarized values should be recorded before restoring power to the rectifier, because then once you turn it back on, you may be able to say the system has shifted enough in a couple hours of the system being back on, and you can pass the system without necessarily having to hit the negative 850 criteria. So here we have a diagram showing just visually what we're talking about with formation and decay polarization of the shift. So looking at formation, say we arrive, the system has been off for a while. So we have our native values depolarized without CP applied. We make our adjustments, we troubleshoot, turn the system on. We have some amount of time that then occurs. We're going to have a shift as the current travels towards the surface of that structure and causes it to polarize. Then we start taking our measurements with our reference cell in the same location that we took our depolarized measurements. If we have a value greater than 100 millivolts, then we have met criteria. But for existing systems with the power on prior to arrival, we'll take our instant off measurements. So we'll be cycling our current interrupter. So we'll have our on value somewhere up here. Then our values will drop down to our instant off values. We'll fully turn the system off. We'll let it decay for a while, usually a day or two if we have time, or a couple hours if we're in a pinch. If we're 7 hours from home and we're in the middle of nowhere and we want to go, sometimes if we can get the shift in a couple hours, then we've got the shift. But same thing, we look for the delta being greater than 100 millivolts. We have our decay, we have met the criteria. Now, why negative 850? We've got the theory, we've got some standards, but why has negative 850 been accepted as the number that we have to hit in general for the instant off criteria? It's the number you see a lot. 100 millivolt shift isn't seen as common, so if you're an inspector, if you're an owner, typically you're seeing this negative 850 criteria, so we'll see why negative 850. Here we have the practical galvanic series in seawater. This just represents relative voltages of all the different typical metals that we'll see in practice. The number we want to look at is right here. So clean carbon steel right from the factory, negative 800. So that's a good indicator. That's our most anodic, the most anodic value that we are going to see in the field in general. So that's the number that we're going to have to hit in order to create the potential differences to stop occurring from our anode. So if our cathode is negative 850 and our anode is negative 850, then we can't have any flow, so we don't have any corrosion. This is when you're kind of have to take my word for it, but laboratory tests have basically shown that in general the most active anodic site on new steel will be about negative 850 CSE. So for cathodic protection is said to be achieved when the surface of the protective structure is polarized to the most active anodic site. So again, without a difference in surface voltages, current will be zero, and therefore corrosion is zero. We're going to bring back in the visual learning a bit again. So if A stands for anode and C stands for cathode, the anode will always be more anodic, have a higher potential than our cathode. So we're going to have a lower spot. So current flowing from anodic spots to cathodic spots on a metal surface. So we have our electrolyte above. We have a metal plate. The entire metal plate is the substrate, which is our connecting point. Our interactions occur at the boundaries of our electrolyte. So current flows from the anode to the cathode, anode to cathode. Reduction reaction occurs at the cathode. Oxidation occurs at the anode. And this is all by definition in our electrochemical cell model. So we have all of these little currents jumping around. So if we go back to our grain boundary structure, this is all what's happening. If it rains and we have a little bit of water available, current is allowed to flow and we get all these little charges going on. So now, taking what we've learned, if we can zero this out, then we can stop the corrosion. So with CP applied, if we think back to our dam picture, current flowing from an external anode to the metal surface. So yellow lines represent current flowing through our electrolyte, which is blue, going to the surface of our metal. The anode is the giver of electrons. The cathode is the receiver of electrons. So then if you can just think of that in the general sense, if you were to be giving a negative charge to something, then in essence that value should become more negative because it is receiving a negative charge. So that, and once we hit this negative 850, if this was the most active anodic spot on a steel was negative 850, we've now essentially filled in the holes of that river valley system of all the highs and lows. Now we have one flat plane of all of our potential differences are equal. They're all negative 850. We can't have any flow of current because we are now providing additional current, additional charge from outside of our system. So we're creating a micro cathode anode system, and we are changing that into a macro cathode anode system. We've got theory, we've got criteria, we've got little fundamentals on Y850. So now let's see how we practically apply CP to metal surfaces. The two general types of systems that exist are galvanic and impressed current. So the anode is our electron giver. The positive, we have our metal connection and we attach it to our tank or our metal pipe. We get flow that way. Impressed current, we have our anode positive on one end, but instead we have a box in the middle that does some stuff. It's connected to our tank. We still have the current flow. We'll see how all that works in a second. Galvanic CP characteristics. We have a fixed amount of current based on the weight of the anode material that's provided. So a larger anode, more current, usually a longer life system. Lower current output though than impressed current systems. It's generally for systems with a current requirement less than 1 amp. So the current requirement is the current needed to sufficiently polarize the system to meet criteria that we have determined, 100 millivolt or negative 850. So for galvanic systems, that a relatively low current requirement, less than 1 amp, is all we can practically achieve. We have a direct attachment system to the structure. Since there's no power source, it needs to be constantly connected to our structure that we are trying to protect. Again, the benefit is we do not have a power supply that we have to worry about. USTs protected by galvanic CP are pre-engineered to account for lower current output. Coatings reduce the current requirement by isolating the metal from the electrolyte. Coating damage during UST installation will cause early failure of the anodes due to a higher than anticipated current draw. Coatings that are non-fiberglass will also degrade over time and will require more current as they age. Electrical shorts cause more serious issues for galvanic systems than impressed current systems due to the limited anode current output. If a system is shorted to, say, the electrical conduit, then that will be a greater surface area required for protection than the initial engineered surface area of the tank, which has a well-coated structure, as opposed to a bare steel electrical conduit system. Anode material is either magnesium or zinc alloy. Open circuit potentials are negative 1750 millivolts for magnesium and negative 1100 millivolts CSE for zinc. For magnesium, this is for a high potential output. There are other alloys that may be less. Zinc is 90% efficient while magnesium is only 50% efficient. So when you're in the design process, only 50% of the anode weight will actually contribute towards CP polarization. Magnesium is the primary anode choice for most UST systems due to its higher driving voltage, right there on our practical galvanic series. A higher driving voltage is useful in overcoming high resistance backfill environments like pea gravel, which are routinely used to backfill USTs. Galvanic anodes need a low resistance backfill in order to function properly. Backfill for magnesium anodes is made up of 75% gypsum and 20% bentonite with 5% sodium sulfate. Zinc does not use the sodium sulfate. For zincs, we have 50% gypsum and 50% bentonite. This backfill helps to prevent metal surface passivization on the magnesium and holds in moisture to decrease electrolyte resistance. Again, with magnesium, the voltage output is so high, we actually get a film that develops over the anode, and that sodium sulfate breaks down the film and allows more of the anode to be consumed for protective CP current. Spike or drive-in anodes on the right are applied on turbine and piping and dispenser areas that are shielded and need a very focused amount of current. These anodes do not have special fill around them. So here we have a general galvanic anode design, starting with our solid copper header cable. The end will be attached onto our structure that we want to protect. The core rod for electrical contact with our metal, zinc or magnesium again. And this rod will most likely extend through the length of our metal block so that the life of the anode will be extended. The cloth bag ensures that the fill stays around the anode. If we have it shift during installation, we want to make sure that it's even as much as we can. We want to moisten it with water before we put it in our hole as well. These are just some example pictures of anodes that have gone on the ground. Got our spike anodes on the side. This is a 32-pound high potential magnesium anode, freshly out of the bag. Again, that would be wetted before we put in the hole. This is just another 9-pound anode on the side. You can see kind of the shape of the magnesium anode starting to come through, even a little bit of a hole. It's probably rough taken out of the package. It looks like it's about 20 inches. You can order a variety of dimensions of anodes. The dimension of the anode will affect the current output since it is a function of surface area for the current production. The anodes that are installed for Type 3 USTs can last 30 plus years. When installed properly, they are easy to test and relatively easy to upgrade when the original anodes fail. When a Type 3 UST needs new anodes added, they are typically connected via the factory structure test lead. If the factory test lead has been destroyed, then a new structure lead must be attached to the US body. Thermite welding, pin brazing, or mechanical screw can be used to attach a new structure lead. Continuity of the test leads need to be verified after installation. This was not my project, but I was driving by and I saw the tanks coming out of the ground and I couldn't help but take the chance to get a couple pictures. You can see the little Type 3 logo popping out on the side, but for new inspectors or anybody that has not seen a tank come out of the ground, this is a great example just to see what they look like before they go in. Obviously these ones are coming out of an old system. These tanks are probably 25, 30 plus years old. You can look at the coating, they look pretty great. The CP looks like it did its job very well. You can see the picking eyes attached to the tanks as well. That would be a good spot to attach a new test lead in the event of a test lead failure. So this one was my project. We're down in a hole at the base of the tanks. We've got our welded on magnesium anodes. So this is how they are attached to the tank. They've just got a bar that comes off, anode on, and done to the tank. So with these, there was a failure of the test leads. So we went down. We could not find the picking eyes. I believe there was some new concrete that was installed, and we had soil access to the side. So we determined it was easier to excavate out of the soil than break to the concrete. And we attached some new test leads. We used a double test lead system so we could verify each test lead with their own continuity. And yeah, this system worked out pretty good. This was an upgrade from a Type 3 tank to an impress current system, and the current requirement is very low for these tanks. So one more diagram of a Type 3 tank. We're going to have our magnesium anodes welded onto the lower quarter, lower fifth of the tank. All of the risers have or should have dielectric bushings installed on them while the tanks are going in or from the factory. So this will isolate the tank from any other electrical systems, The anodes then will only be protecting the tank body. There will be a factory test lead that will be wrapped around one of these risers. You can see it's zip tied is the most common attachment. Over time, the zip ties can become brittle and they'll break. We'll have next slide will show a larger picture of that test lead so you can get an idea of what you're looking for if you're out on inspection or if you're an owner trying to figure out if you have Type 3 tanks. So this is the enlarged structure of our Type 3 test lead. You can see that the coating on this one's a little bit damaged coming out. So this is the structure part of the tank. So this will actually receive protective current from the anodes since it is exposed. So that's not too much of an issue as long as we don't lose continuity with the tank structure. We can verify continuity by testing the tank bottoms unless the tank is lined, and then we cannot get access to the tank, and then it becomes very difficult to determine continuity with the tank structure if these test leads are damaged. This will be another indicator that you will see for Type 3 tanks. These will typically be buried right next to wherever the test lead has been installed. It's got some nice little diagrams that tell you what's going on with the test lead. It's got the instructions for monitoring. So if you see these buried next to a tank, you more than likely have a Type 3 tank on your hands. This is another alternative test lead method that you may find in the field. So we do see our Type 3 tank little tag hanging out, but this is the structure test lead. I think this is just an older school method maybe of doing it. This is just a way to be more of a standalone than using the zip tie method. Just as effective. If anything, it's actually better because it will use its own hole. It'll keep the structure lead away from any monitorizers and possibly have a short. Sometimes if an installation crew is a little rough with the wire, you never know, something might get exposed and you might get a contact with the riser and you may have an early failure of your anodes. I think that covers about the general gist of galvanic cathodic protection. Let's move on to impress current cathodic protection. So we'll start off with another definition. An electrical current supplied by a device employing a power source that is external to the electrode system. So this uses a rectifier that converts alternating current into DC current. You can also have rectifiers that are solar powered. You can use natural gas, or you can use any kind of fuel, energy source that is available. If it's on a pipeline, you can siphon off a little fuel. You can power a rectifier, but that is not seen in the UST industry since we're just using 120 most of the time. Asphalt resurfacing is a common cause of broken cathodic protection cables for these impressed current systems. And if there is a retrofit galvanic system, should have included that in the last one, then that could also be another cause of failure for systems. So the anodes for impressed current systems are made of material that are more resistant to corrosion than galvanic anodes. So right pictured below, we have some mixed metal oxide anodes. You can also have high silicon cast iron, and these are the most common type used for soil applications. And for impressed current anodes, we have a special backfill that's called coke breeze. So it is specially treated carbon that acts as a low resistance fill to surround the anode and ensure contact with the soil. So we make our hole and we backfill around the anode. So almost like a galvanic anode with select fill bag around it. Instead, we backfill with this coke breeze, which is also conductive. So electrical current will flow from the surface of the anode through this coke breeze. Then you have an oxidation at the edge of your coke column. So you effectively make your anode column larger by adding this coke breeze around your impressed current anode. So I mentioned in the other slide, you want to use a material that is more resistant to corrosion for impressed current anodes. And right down here we have the high silicon cast iron, carbon, and graphite. So carbon being our coke, high silicon cast iron is the other metal, and mixed metal oxide would also be right around here, as opposed to the magnesium that's way up here. So since we're forcing current through these anodes, we need to be really conscious of the corrosion rate, since we're essentially forcing more current through these, and we can adjust the voltage output from these over time. So we want something that's going to be more resilient to differences in voltage. With impressed current systems, we have the possibility for stray current effects. This should be accounted for in your design process. With nearby metallic utilities, they can pick up current from UST ground beds or anodes. We can use ground beds and anodes interchangeably. And then these urban areas, though, it may be impossible to avoid interfering with other utilities. With the impressed current anodes, they produce a voltage gradient, and as long as a utility exists within that voltage gradient, it is susceptible to pickup. The utility will receive free CP, essentially, where the pickup occurs, but downstream, where we have the system becomes electrically remote and then begins to try to return and finish the circuit, we will have current discharge, and then we will have accelerated corrosion on that utility, and if it's a natural gas line, we can put a hole in the pipe if we're not careful. So electrical isolation could avoid this, it could help, but it's usually not practical or economical for UST systems. The best solution is typically reducing the rectifier output and evaluating the system on the 100 millivolt shift basis. So we were trying to reduce the voltage gradient of our anodes, and we're trying to reduce the current output. So we know we're going to have problems, so we're just trying to make our problems as small as possible by basically going with a lower current output. With impressed current, there's just all kinds of problems you got to account for. And another one is the corrosion can be accelerated if the leads for the anode and the cathode are switched. So the elements of the electrical chemical cell are reversed, and oxidation will now occur on the tank, and reduction will occur at the anode. So when you're out in the field and you're taking a survey, a positive value may be recorded if the leads have been switched. Reporting the correct polarity is very important for this reason. Do not leave out your symbols on a report. So for an example, a value should be reported as negative 850 millivolts CSE or negative 0.850 volts CSE. The leading zero should be included for clarity if you are using volts. A value of positive 0.850 volts would indicate that the tank/pipes are electropositive and that there is current discharge at that location, which is a very big problem and should be addressed immediately. Significant electropositive shifts in potential readings from previous surveys are an indicator of current discharge at the locations. So I put the word indicator because that's all it is. Further testing should be done to verify the situation on the tank if you find those readings. This is a slide I may get some pushback from other people in the industry, but from my experience out in the field, the current required for protection of USTs is generally 1 amp per 10,000 gallons to achieve negative 850 millivolt CSE Instant Off. And again, I want to highlight this is a general criteria, not a fixed rule. So this is what I've kind of seen through in systems over the years. This is for the Pacific Northwest. Every region will vary, moisture content, soil content, clay, gravel, everything. It's very different. Maybe there's different anode layouts that are more regional than what I've seen here in the Pacific Northwest. So my experience is limited to Oregon and Southwest Washington. So then, but for an example, if we had 3 12,000 gallon tanks, non-metallic product piping, we would expect to see 3.6 amps for adequate protection coming out of the rectifier. This is mostly for inspectors that when they look at a system, they want to know if the system's good or not. And for the relative size of the system, this is probably what they should expect to see. And if an inspector has been doing it long enough, they would probably agree with me and see similar values. But these situations are highly variable. This assumes well-distributed anodes. An anode can only protect essentially what it can see, so we need to encircle our tanks, and that's part of having a well-distributed system. If we were to adjust to a 100 millivolt shift, I have seen historically in the past that about 1/3 of an amp would be enough to protect a tank and shift it on the 100 millivolts to get us to meet criteria for that as well. Galvanic systems can be upgraded to impress current. There's nothing really stopping you. It all comes down to current requirement and budgeting. Galvanic systems are cheaper to install, lower maintenance costs, so that's what you want to go with first. Impress current is kind of the big dog that you don't want to use unless you have to, also for the straight current effects as well. Current requirements for these systems that have been upgraded, so say a Type 3 tank, that can be below 0.1 amps per tank. So this can make it difficult to accurately measure the output on a visual amp gauge on a rectifier. So if you're an inspector or if you're somebody taking down your log sheet, you may have a system, if it's a relatively large amp output, if the rectifiers say been missized, if you have a 40 volt 10 amp rectifier and it's only producing 0.2 amps, you may not even see it register because of the coil may be adjusted too high, and if you turn it off, it may not even move. So you may have to take a shunt reading. To get the most accurate readings off of a rectifier, so a direct reading across the negative and positive terminals measured in volts DC will provide the most accurate measurement for voltage output. And I was just talking about on the other slide, a shunt reading. This is measured in millivolts DC. Notice we have a difference. Millivolts and volts, two different settings on your multimeter. This will be the most accurate way to measure your amp output. The shunt rating must be known to convert the readings into amps DC. A typical shunt is 10 amps 50 millivolts, which then if you simplify it, 1 amp per 5 millivolts, we simplify again, would give us a conversion factor of 0.2 amps per millivolt. And I'm just doing 1 divided by 5. That's how we get that number. So as an example, if we have a reading of 12.5 millivolts on this shunt, our amperage would be 2.5 amps. There's the math. A couple examples of shunts. That's a 6 amp 50 millivolt, 10 amp 50 millivolt, 15 amp 50 millivolt. They're pretty standard. You get your alligator clips, you take your reading, make sure that you're in millivolts DC when you take that measurement. Now let's move on to the brains of an impress current system essentially, and that is the rectifier. So for the UST industry, we're going to see constant voltage as the most common one. It has a fixed voltage, which can only be changed by modifying the tap settings. Tap settings typically have coarse and fine bars. The taps are connected to an internal transformer in a rectifier. So we're gaining more access to the transformer. Remember, we're taking AC and we're converting it into DC. There are dial adjust rectifiers that exist, and they use a rheostat for variable resistance. These are on older school, usually Goodall rectifiers, I believe is the ones I see them on most. And for these, if you have your little form setting, that you'll see C1, F2, coarse or fine, there will be no way to select that. There is constant current, which has a constant current output. It's not common for USTs, and constant potential. You bury a reference cell next to a pipe, and that rectifier will adjust based on what potential reading it has off of a permanent reference cell. But again, these last two are not common for the UST industry. Rectifiers are typically solid state in their operation with only a few moving parts. Typically the clock gauge would be the only moving part. This allows for long-term operation with little maintenance. It is not uncommon to see rectifiers that are 30+ years old in good mechanical shape. It is important, though, to keep accurate rectifier logs in case troubleshooting is required. Rectifiers should be placed in an easily accessible spot. If it is difficult to open the cabinet, it is more than likely that 60-day readings will not be recorded. I see this all the time. Put them in the back stock room, get a bunch of boxes in front of them. They're installed up high, somewhere awkward. People forget they exist. You have turnover in your building, and the readings never get done. And then a year later, somebody comes by, you have an inspection, and you find it's off, and you have no idea how long it's been off, and you got problems. Rectifiers need a dedicated circuit Should always be left on unless damaged. If there's a short, if there's electrical damage that's visible, call a technician, get it checked out. The rectifiers placed outside should be padlocked to prevent being tampered with. And we talked about the possibility of the wires being switched. If the polarity is switched, you can cause damage to your tanks very quickly. The units that tend to collect dust should be cleaned with compressed air periodically to prevent overheating and early failure. Just like most electrical items, they can be 1, 2, or 3-phase. 3-phase units are the most energy efficient, but are also the most expensive. Typical gas station units are only single-phase. A broken wire in either the anode or structure cable will cause the amps to drop to 0. A rectifier with the same volts as the previous month, but no amps, has a damaged cable in the external circuit. The DC fuse may also be blown. If a fuse continually blows, there may also be additional issues with the rectifier. If you go to do your 60-day check, there is no volts, no amps. It means that external AC power to the rectifier has been lost. Check the circuit breaker to see if it has been tripped. Continually tripping of a circuit breaker may mean that there is a short in the rectifier. An AC fuse may also be present, which has failed. The clock gauge failure is common. I see sometimes people make it an issue on their forms that they want to see the gauge run, but these fail a lot. As long as you can see that your volt and amp meter gauges are consistent, you're good to go. And that goes to the next point. The green-red dummy lights that I have seen on some models, they should not be relied upon to see if the rectifier is operational. You should be checking your volt gauges. Those are your primary source. Again, even if your volt gauges don't work, if you become familiar with multimeter readings, you can take direct measurement readings as well for the most accurate data from your rectifier. Next several slides are just going to give some examples of rectifiers I've seen out in the wild. There's lots of them, so they all come in different shapes and sizes. We have the ES1, does not have a volt gauge, only has an amp gauge. Little shunt, have our positive negative terminal, coarse and fine taps, AC breaker. Nice little system. It's compact. Only goes up to 40 volts, 5 amps for most systems. You can get the Cadillac of the ES. You can go to the ES2. You can get a volt gauge on that one. Same thing. Got the amp. You can get an hour meter as well. Shunt terminal down there. Here we have two side by side. This was a split system. We have two different ground beds on one site controlling different set of tanks. The field trip goes on. We've got some old school systems. Yeah, look at that old wiring. All kinds of stuff. Goodall's been around. They got some pretty good units. They're pretty robust. This is a flip down unit. The panel goes up and then comes back down for servicing. So you change the taps right there. And there's, I believe that is your rectifying components as well. This is a very basic overview of rectifiers. If you want to learn more, take a NACE course. But this is mostly just to get the quick and dirty version, really, of CP. You can take months of courses to try and learn this stuff. Another flip out unit. Another set of taps. Pretty interesting. I tried to include a unique one on every picture. This was an interesting model. This one, I believe, had been in operation since the 60s. And was found inside of a mechanical room, still working. Only reason they worked is because that needed to come out was because the tanks came out. Other than that, still works. It's totally fine. This is a unit with individual anode control output. Very fancy. Don't know why it went into a gas station. Maybe they had one laying around, but you can dial in each anode output on its own. It's really nice. Really overkill, but a very nice rectifier. This is the gold standard of gas station rectifiers, the universal GSAI, 72 volt 8 amp, 72 volt 10 amp. You can get it in any kind of configuration. This is probably 7 out of 10 times you're going to see this rectifier if you're doing inspections. Volt gauge, amp gauge, hour meter, tap settings, system information. It's a great unit, and yeah, very common. So this is another older guy. It's a benchmark power supply. Yeah, these ones you don't see very often. Definitely older. These screws come off. The whole unit flips down as well. It's talking about some output adjust rectifiers. So this is 2 rectifiers built into one. Unit 1, Unit 2, output adjust, rheostat. And we have our outputs there. Unique setup. Said if you can dream it, you can do it with a rectifier probably. It's just going to be really expensive. We got hinges on the left. These 2 guys come out, swings outward. We've got our mesh grate on the bottom. These are air-cooled units. So the air is pulled up through the top, causes the unit to get a nice draft. More grates on the top, and then exits out the top end. More examples. These ones has a toggle switch. Actually, there we go. This one has a toggle switch. So the voltmeter and the amp gauge are combined into one. So you got to be careful which one you're reading. Volts on top or amp on bottom. These switches can be finicky. Sometimes they stick. And if you press it for the first time, sometimes you'll get a reading of 0, which is a false reading. If you kind of just literally, you got to jiggle it sometimes to get the actual reading. Because you can take your direct reading, you can see there's a voltage output, take your shunt reading, know there's an amp output, but then it doesn't match up there. So sometimes it's just a faulty switch. The journey goes on. Another kind of just generic rectifier, taps up top. This is probably a bare bones budget. Not a lot of plastic going on, just basic metal casing, rectifying unit, volts and amps, 1 gauge, toggle switch, shunt, terminals, pretty basic. Here's our rectifying unit. This is our transformer out in the open. Got our diodes. You can do a spare fuse, hook up on that one. Spare fuses are present, so this system was probably tripping quite a bit. Probably had some other issues going on. Yeah, that can be another indication of issues with the rectifier, is the several discarded fuses existing in the cabinet once you open it. This unit was sold that the markings had started to come off of it, but again, the basic tap and bar, pretty old. This looks like this was an old lightning arrestor system that was installed. You can see kind of the dust buildup on these units that occur. That's why it's good to hit them with some compressed air. Make sure that you're staying away from the live wiring in the back. That is hot. The switch on the front will control to take off the DC power. So these guys will be dead, but you'll still have live 120 in the back. So don't touch it with a screwdriver like me to get accidentally shocked. Guardian, these units are fairly common as well. They got them labeled for you too. A+ for anode is always a great way to remember it. Structure on the negative. Tap settings, hour, that gauge probably failed. Volts, amps, we got our little green dummy light. Usually those fail as well. The Goodall, this is another rheostat one that I was talking about. So this is a dial adjust unit, 0 to 120. I'm not actually sure what the units are, but they're great little units. Goes up to 50 volts on this one, 5 amps. The gauges are actually curved, so you do kind of got to bend your body around to get a accurate reading on where it's at. AC DC fuse, great little systems. They make really good for test rectifiers because you can adjust the voltage output so quickly. This is a technology rectifier. These ones are unique in that the output adjust is there. We also have tap settings here. I've found the trick with these ones. This is a freebie on me. Turn the dial output all the way down to the left before you make any adjustments or turn the unit back on or off. If you do not, you will cause the circuit breaker to trip almost every single time. So turn it all the way down to 0 first, then turn it on or off, then bring it back up to whatever its operating capacity was. And we got another lovely toggle switch here. Then will prevent the system from tripping. That one I've spent many an hour trying to troubleshoot, and that's the procedure I came up with. So I'm going to kind of go over a quick and dirty example of an impress current anode installation so like again, mostly for inspectors or anybody that's just kind of unfamiliar with the procedure. These are not underground storage tanks, these are above ground storage tanks, but they provide a great visual of how underground storage tanks look underground. If you were to imagine these vents being the top of the sump, your turbine area, that's roughly the same for, let's see, these vents. That's probably about grade to sump for a lot of systems. That's probably 4 feet, so even 2 feet. So imagine all these next to each other. All the steel tanks have flat ends. These ones need a paint job. But this is what you can visualize in your head when you're trying to protect steel tanks underground. This is the order that they will be arranged in. And now that we have that visual of the ASTs, we can look at these USTs and kind of know what we're looking at. So again, our turbine sump, we have about that placement, top to grade. These are our anodes. We want them well distributed. We want them in between the tanks so that the current can travel along the portion of our tank body and just polarize as much of the surface as we can. I have seen proposed systems, we'll get to another top-down view of the tanks eventually where there's a different proposed method, but these are what I see most common in industry, and this is what you'll see if you're out in the field. You'll have all your anodes spliced together. Usually you'll have nicer systems that have individual leads brought up from the anodes, and they'll be brought to an independent junction box somewhere, and then they'll be hooked into a common bus bar. Then that bus bar will have one final lead that will then hook up to the rectifier, but hooking them up in series like this is very common. So this is the top-down view of the tanks. This illustrates our structure connection, typically on the monitorizer. This is assuming the monitorizer is continuous with the tank body. Make sure to check that if you're unsure. So we'll have our connections going across. We'll probably have a common hole at some point where our anodes are going all around our tanks. Again, assuming well distributed. Some systems require 2 anodes on the sides of the tank wall. If you want to be a champ, you can put 3. Again, that will increase your excavation costs, but that is more is better for this case because you're trying to distribute your current more efficiently. Better current distribution we have, the more even our polarization is around our tanks. And from some of my NACE courses, I've seen that they suggest installing anodes in the middle of the tank. That is a pretty scary proposition if you want to start core drilling in the middle of the tanks with non-metallic pipeline that's not traceable, or if you have vent piping that is fiberglass, again, that is not traceable. If you think you're good, you can maybe do it, but good luck if you core right through a vent line and you got to go in and replace that product piping or vent piping. So these aren't necessarily perfect examples, but these are examples of what I've seen in the field. The vent lines back in the day were all metallic back to the tanks, so they had good continuity. They just ran simple grounding collars. You daisy chain them together with a solid piece of copper, and then you take that guy and run it to your negative. This is a little more high end. Got the monitorizer brushed off, 4-inch aluminum cable or aluminum ground, and that would be daisy chained back to your rectifier. This will be a little quick slideshow on an actual step-by-step of one install that we did years ago, kind of just as a general layout, because everything kind of went pretty clean on this one to show it. So we got our anode squares. We got to cut them out. We got to make way for our truck to get through and make the holes. All these dotted lines is where we're going to put our header cable, get them all attached. So we got to break through the asphalt. The asphalt can be pretty thick. If you don't know how deep it is, you may have had multiple layers. Could have an old station. Could be up to 8 to 10 inches of asphalt if you're unlucky. So once you're through the asphalt, you've broken through any kind of random concrete, and assuming you haven't hit any vent lines that were untraceable or any other kind of fun things that were present in the hole, we typically use hydro excavation. Just use water and air to excavate the hole because, again, it's pretty safe. So you come across a non-traceable utility, non-traceable product pipe, you can just move the hole if in the event that you do come across it. This one was clay. It was a great hole example. So we got all the way down to 10 feet. The tank bottoms, I believe, were at 9 feet. So we were overachievers, went down a little bit deeper, and we got all the way down. So made great anode columns. So here's a picture again with the coke breeze. This is the amount of coke breeze that we put in the hole. 6 bags for a 60-inch anode. Put it all the way down to the bottom. Fill her back up. Have some coke on the top and bottom. Give it a little bit of a buffer. We got our splice kit ready for some resin on the side. So this is kind of a standard anode column design for me. 14 inches is pretty large, but that's assuming that if the event you get unstable soil, sometimes the anode column gets a little large and you got to use a lot of coke, which isn't a terrible thing. It will cost a little more for backfill, but you will have a large anode, which will reduce circuit resistance. So in that event, you actually will get quite a bit of current output out of that anode. And for UST systems, they can require a large amount of current. So sometimes it's good to just go big on these ones, and you can start out low with your Impress current system and dial it up as needed. It's kind of a little step-by-step on how we do some splices. Little compression kit. I know you can solder them. You can do hammer molds as well if you want to get that really good connection. We've got our plastic kit. These are 3M kits and 90 B1Ns, I believe. You bring some extra electrical tape. The wire they provide, or the tape they provide, and the kits are no good. They do not seal. Take your packet, pop it, mix it, and pour it. It'll set. It'll get hot. You'll have a great splice kit. Make sure you fill all the way to the top. Don't leave any voids. This is an example of some series splices I had to do. Multiple anodes coming in from different angles. Just got to bring them all together, get them spliced up, and then home run it back to, I believe there was a junction box on this one that we were using. But these are all anodes. Tape them for red. Make sure to keep track of your wires during the installation. Sometimes when things get underground, they get muddy. You can kind of lose track of things. So it's good to have job site record keeping when you can. Once you got them spliced, got them patched, got the wire run, backfill with some material, soil, something good and conductive, and you put your asphalt patch on, compact good, fill it with some mortar, and you're off to the races. So vertical anode columns are not the only kind of column. So here's a little overview of some other ones as well. So if we use the word vertical, that implies that horizontal exists, and it definitely does. If you have the access to the soil, you can create a trench, you can dig down, and you can layer anodes like this exactly in a vertical fashion, just in a horizontal manner. And this effectively becomes one giant anode. So you want to put anodes in periodically enough so that you have good current distribution and that your coke bed is active. But yeah, surrounded by coke, you get effectively one giant anode. Works pretty well for current distribution in the right situation. Some pictures of a horizontal coke bed going in, looking like that. Got some anodes laid, coke, compact, backfill, moisten, fired up, you're good to go. So you can have a super vertical anode column, essentially, semi-deep well, 25 to 50 feet deep. You'll have the current produced from all sections of the active coke column. You'll cap this off at some interval that your engineer will call out, but you can have current travel all the way from the bottom and come up and protect these tanks. Now I say placed in remote earth if possible. So if we just follow Ohm's law again, if the resistance from these tanks is all equal, because if we've reached remote earth, or basically we are considering the resistance value is no longer changing on the voltage gradient of our anode, then the current distribution will be equal on all these tanks as well. For urban areas, this can be hard to achieve, but you can achieve a remote earth by just simply going deeper and having your anode placed further away from your object, which we'll see next. So if we have semi-deep well, we have deep well columns. These ones are placed 50 feet or greater in the soil. These can be several hundred feet deep. These are typically for wells for oil and gas. But if you have a highly urban area and you have a very distributed natural gas system, say, and you cannot retrieve a remote earth by going laterally, you can go down. You could have a couple hundred feet, or as long as your engineer requires, as long as your equipment can go, you can place dead zone and you can achieve remote earth by going down and away from the grade. And then you can have great current distribution spread throughout your system that way. So these are just some pictures of steel tanks that had impress current CP on them. Again, I think these were 30 plus, 40 plus year tanks. So just a good field trip, just to kind of see what they look like when they come out of the ground. Again, looks like the CP did their job. They look pretty great. We've got some deposits that have built up on the surface. Another angle, little nodule built up. But overall, the tanks look pretty good. Doesn't look like there's any bulge in them. Look pretty structurally sound. Nice close-up of the edge of the tank. You can see where there's been materials kind of scraped away just to reveal the contrast of what was there. But looks really good. Nice defined edges. And tank is up and pulled, did not buckle. So you can tell there's quite a bit of strength left on the steel. Just wanted to kind of touch on some survey equipment and measurement techniques for inspectors and others before we finish up. Copper sulfate half cell. This is the workhorse. This is what gets your readings onto paper through your multimeter. So they're portable and rugged. You can tell this one's got some pretty good use on them. Industry standard, so it must ensure that the internal solution is saturated for stable readings. So you can do what's basically called the shake test. You should be able to hear crystals inside the reference cell if you give it a good shake. Measures surface polarization in roughly a 30-degree angle. So if you can kind of imagine this cone coming out, that's about what it can accurately measure. There is also an internal copper rod that must be cleaned periodically. There's a little bit of buildup that will happen on that. You want to use a non-metallic scrub pad so that you don't get any extra metal ions built up and cause false readings on your reference cell. So this is a current interrupter. This is the one I use, CI50 from Tinker and Razor. There's a lot of current interrupters out there. This is not the only one. You got the program settings, the seconds on, seconds off. It's pretty nice. Set it, forget it. Basically, it acts as a light switch for the rectifier. You get your cycles. So for me, I do 10 seconds on, 1.5 seconds off. Some people do 5 to 1. You can do 3 to 1. I think you want to go at least a 4 to 1. 4 seconds on, 1 second off at kind of a minimum, because you don't want the system to depolarize while you're taking your measurements as well. Your multimeter, the thing that actually records your data, is very important to not cheap out on. See, and I use the higher end one to try and get accurate data. There needs to be an internal rating of 10 mega ohms. So this high internal resistance is used to reduce measurement error. There's some math behind this that if you take the NACE courses, they'll show you and they'll tell you why you need that 10 mega ohm rating. But there's external resistance values that will start to become a big deal and mess up your measurements if you do not have a quality instrument. Here's an example of having a quality instrument versus a poor instrument. If I had a non-quality instrument, this number would be 850. But because I can see an extra significant digit, to me, I can see 8499. If you had one meter that could only do 850, then you may have a false reading, or you could maybe even have a failure, depending on how picky the inspector could be. I'm sure some people will push back on me and say, oh, that doesn't matter, you're being over specific and you're being too picky. But the number exists, we can measure it, and it's there. So it's just an interesting little factoid to bring up. So this is a video, if we can get this to play. showing exactly why you want a good meter. So we have our on reading, our current interrupter is cycling. You'll see it drop to some value. Looks about 850 from the eyeball test. I don't know if you caught that. Now let's zoom in and see what it actually was. So you have your reading, your drop off. So 880 is what the instant off measurement was for that. Now let's see it again. See if you can catch it. Was that 880? If you had a poor meter, you may not have been able to actually have caught that. This is available on our Facebook page if you want to watch that again. Other basic equipment is just your wire reel. You probably want a couple 100 feet, because for some systems you're going to be going pretty far from the rectifier to the tanks. You need to get a remote reading. Hand tools, screwdrivers, lid pullers. Make sure that you're being safe. Don't be pulling your back with those heavy lids. Water jug for your reference cell. Sometimes you're going to have dry pea gravel, dry soil. You could have sand backfill depending on the area that you're in. You want to wet the surface to avoid a high contact resistance that can introduce an error. Again, another reason why you need that 10 mega ohm rating on your multimeter to prevent measurement error. Extra batteries for meters. It really sucks when you're out at a survey and you run out of batteries and you got to go back to the store, get the batteries real quick, and in order to keep working. Spare reference cells. You should probably have several. I carry at least 3 on me at any given time. I have a nice one, a beat-in one, and just another one. You have one at the office that you can use for calibration as well. Little quick snippet on some measurement techniques. So while you're measuring, the reference cell needs to make good contact with soil to limit measurement error. Soil gravel can be wetted to reduce high circuit resistance that is possible with a reference cell. The factory test leads for multimeters should be replaced with alligator clips. If you're in the field and you're trying to push your reference cell down and get good contact, those little leads that they give you will pop right off all the time. So you want to get something that's durable, that you can actually have some faith in your test leads. Extreme temperatures can affect reference cell readings. Cold days will increase readings, hot days will decrease readings. The temperature of the water and the reference cell is the dependent variable. Because we'll have the water temperature affects the solubility of the copper sulfate. If you take the class, you'll do some work on some Nernst equations, and you'll look at the solubility of the solution. If the solubility of the solution is not stable, you will have a drift in your reading. And exposing the reference cell window, so there is a window that you can look at your liquid inside, see if it's clear or not. That if that's in the sun, it will also affect your readings as well on your reference cell. So impress current anodes can be located by placing a reference cell on the ground and moving the reference cell in the direction where the on values go higher. So all we're doing is we're tracking the voltage gradient. It's pretty straightforward, but in areas just like this, so it can be useful for locating anodes after resurfacing has occurred and assuming the cables are intact. Sometimes you get resurfacing companies that specialize in gas stations. They run into these wires and they kind of know how to handle them. But then you come back in 2.5 years after you surveyed the system and there's a new parking lot and you have no idea where anything's at and you're trying to troubleshoot anodes. You can't see where anything's at. Sometimes this is a good technique to have in your back pocket. And also, exposed sections of the cable will also show a voltage spike in the anode circuit, because in any exposed section of wire in the anode header cable will become an anode. This accelerated corrosion will eventually cause header cable failure. A lack of a Type 3 test lead is a massive measurement issue. You can get around this by making contact with the tank bottom, usually through the fill. You can also do the monitorizer. Sometimes there can be strike plates in place with a fill though, so you may have some continuity issues with there. But this also cannot be done if the tank has been lined. So if the tank has been lined and you don't have a Type 3 test lead anymore, you're in pretty big trouble trying to determine continuity. Limiting the IR drop, it's kind of self-explanatory. It is an error. You need to be conscious of it. You need to know where you're testing, kind of what's going on with the system. That kind of just comes from experience. Lack of soil access above the tank. Sump rings may be tight, may not have enough room to actually get to the soil, get to the gravel. There may not be monitor rings installed along the length of the tank. Maybe that's an old system. Maybe it's a siphon tank system with no turbine system or no turbine setup. So you only have a fill and a monitorizer, and the rest of the third of the tank isn't available for reference cell access, and that can be pretty tricky. Might have to drill holes to try and get through it. So accuracy of meters, cheap meters, it's bad. The lack of accurate records. People lose station records for UST systems at gas stations all the time. It's pretty rough. Again, that just rolls right into lack of records in general. Just kind of a practical thing. This is an on reading of a gas pipe. This is a propane line. Got the reference cell jammed up right up against that pipe as tight as I can get it to try and reduce that error. So I am taking an on reading, but I've got 1100 millivolts. That's pretty good. If I was at negative 850 and I was only at my on, then you got to start wondering if this system needs new anodes. This is a basic setup for how it would look with my rectifier. I've got my anode disconnected. I've got my tongs plugged in for my interrupter, and I've got one unit on there and hooked up to the terminal, and we're cycling, and that's just kind of my multimeter hanging out. I just kind of wanted to provide an example of a galvanic report. I've seen varying levels of reports over the years. Some of them have been fairly bad, and I just want to try and show maybe what could be presented. This isn't necessarily the only way to do it, but it's how I do it. I just wanted to provide that for other people to see if you're starting out, or maybe inspectors trying to look for other reference material. So I try and get a reading on every third of the tank if possible. Again, sometimes the soil access is not available. I want to measure or mark where I'm testing next to. So monitors, turbines, fills, vents. Want to indicate where your remote is, landscape area. So you're telling me it's soil. If we're got some parking lot area, this is kind of just a general. These are stipe tanks, so indicate where the test leads are. Again, I could even be more specific and say stipe 3 test lead for which one. I've got the tanks labeled, and just trying to give as much data as I can so that if I had to come behind and replicate this test, it would be very simple to know where exactly my reference cell goes, what I was attached to for my structure, and which structure I was testing at the time. So this is an Oregon form for their UST-CP stuff. So I just use Oregon's form. And this is for that same system we just saw. So R1, R2, R3, which test lead I was attached to. Here's my readings with the proper polarity reported in millivolts with the type of reference cell that I was using. There are multiple types of reference cells that you can use. In most cases, you're not going to be using anything else other than this, so people assume it sometimes, but it's good for completeness to include that. Just let people know that, yes, I indeed was using a copper sulfate electrode. It was negative, and I was using in millivolts. Just kind of mention that criteria I was evaluating. Remote, there's my numbers off to the side. So for an inspector note, the highest reportable value should be negative 1750 millivolts CSE on for galvanic systems. So we consider this because this is the limit that would be for a magnesium anode. It should be the highest voltage that is achievable, because then once an anode is connected to a structure and is under load, then that value is going to go down. So if you're seeing a value of 2 volts negative on for a galvanic system, you might want to start questioning stuff, saying, how did you get that number? And are you sure you had good continuity? Are you sure the anode is connected? You could be just testing an open circuit anode voltage that's not connected to a structure. For remote readings, I have a bone to pick on this one a little bit. I believe that remote readings are not a measurement of surface polarization, because you need to have your reference cell over the structure you're measuring in order to have an accurate measure of polarization. Type 3 includes it in some of their standards, or their standard, saying you need to take a remote reading. I take it because they say so, but by definition, a remote earth reading is a point where the voltage gradient is no longer changing. So if an inspector could get back to me in the comments or something on that, and then I'd like to have that cleared up on why a remote reading is a indication of a fail, or why it needs to be included in reports. I think, again, I do it, but just curious. All right, moving on to the Impress current report. So we've got 3 tanks, we've got some piping, got a lot of metal on the site. So we've got our rectifier, our transformer rectifier, that's what TR stands for. Vents noted, gravel, monitor wells, tanks indicated, little extra lids on site, monitors where we're at. We're on gravel. So for our reference cell, we're at the edge of the tank measuring through gravel. So we've got good contact with the electrolyte. Tanks are labeled. Reference cells are numbered. We can go back and we can repeat these values. Reference cell is placed inside the dispenser next to the piping. Try and get right next to wherever the surface is being polarized to get that measurement. So again, we're using an Oregon form for DEQ. Just got the basic rectifier information. Got our as found, as left. So on this one, I picked this one specifically because I did a 100 millivolt test on it. So I left it off for a couple days, came back, and it got new values on it. We'll address this as well later on. But yeah, make sure you're reporting your values. If there is an hour meter that's functional, make sure that you're reporting that as well. Oregon DEQ, you guys need to make your listing bigger. You gotta have more slots for measurement data. So since I had so many measurement points to take, I had to basically just make my own form, just make sure we got all the pertinent information. Structure we're testing, where we touched, half cell location, where it's at, on potential, instant off potential, depolarized potential, and then reporting, just doing the math for the 100 millivolt shift, making it simple. So we can scroll down and we can go, okay, everything's above 100 and we're good. So we got one little guy that's close to 103, 109, 109, but I got 500 millivolts difference. 1169, that would have passed the 850, but that was probably right next to an anode. This one would probably have the anode starting to fail, starting to be not so good. Piping, all these values, yeah. So your on value is going to be higher next to your anodes. So you can have strong anode values. That's probably why we had strong polarization. The lower the anode, the lower the on value. We talked about the IR drop and being able to calibrate it. After a while, you can kind of get a feel. You put your reference cell on the ground, you can see your on value. If you're already several measurements into a site, you can kind of anticipate what your instant off value is probably going to be after that as well. This is a basic rectifier log sheet. Facility name, amp range recorded, volt range. These can be valuable in case there is a shift. For the amp range, that should be the only value that's really going to shift on you. You can put a range 100% plus or minus of what you got going on, just to prevent erroneous service calls. But really, you're looking at 0 amps is going to be your big one. If you're producing 3 amps, then it goes to 0. That's a big issue. If it goes to 3 amps to 2.5 amps, it's probably just dry soil. Basic information, extra stuff down here, just kind of really basic. As long as you have something that shows that you're taking measurements, that's about all you need. Additional notes, this is pretty getting more in the weeds, but just figured to put it on here. On values will be higher next to anodes. Depolarized values will vary. They can vary greatly. So measured values in the field have ranged from -150 to -750. Most will average between -300 and -500. We go back to our practical galvanic series. New steel is about -500 from the factory. So over time, the value will decrease. We'll become more electropositive. We'll lose that energy built up in our lattice, and we'll approach values closer to -300. So high, low off values may be interference from CP systems. So you can have at the value where we have a high off value, we could be receiving free CP on one end of the tanks from another system, and it could be discharging. So then if you have low values on the other end of a tank, then you might want to start looking a little harder, maybe call somebody in. Amp values on 60-day log sheet will have a seasonal variation, like I talked about, due to soil moisture content. If you're in an area with high groundwater influence, this will be even more pronounced. Amp readings for systems with new anodes will decrease over the first week. This is due to a transition period of activation polarization to concentration polarization. Again, I'm not really going to get into the specifics of that, but due to the characteristics of how a system polarizes, you'll have higher amps on startup, and then basically the system will reach a steady state, and then you could go down to say 3.5 amps a week later. These are some personal considerations for the future of CP in the UST industry. For permatanks, I would like to see them start to be tested, or maybe just some examples done to see if they truly are good. These are fiberglass wrapped steel tanks, which are currently exempt from CP testing. And if you take a coatings course, they will tell you that no coating is perfect. Even if it's 99.99% effective, there will still be a flaw somewhere. And at a holiday, you have corrosion current concentrated. So if there were to ever be a failure in permatanks, there would be a rapid failure of that system. Inclusion of test coupons for STI P3 tanks, Type 3 tanks. STI, if you're watching, you should maybe check out some test coupons. Coupons are very widely used in the pipeline industry for systems that have welded anodes that can't be interrupted. So you can interrupt the test coupon as opposed to disconnecting the anode system that can't be disconnected. You can get some more accurate information for those. Just like this video, increased general knowledge of proper application of CP for UST owners, stakeholders. Basically, there's a lot of people that have considered CP black magic. You don't see it. You don't know what's going on. You have a guy show up once every 3 years at your site, tells you pass, fail, and you don't really quite know what's going on. So it was kind of my motivation to do this video, to try and get a little more knowledge in the industry to kind of demystify things. And I would be interested in seeing an implementation of a standard CP testing form accepted in all 50 states. And the goal would be to help standardize testing procedures nationwide and make data comparison easier from tester to tester. Thanks for your time. We've reached the end of the slideshow, and I just wanted to add some fun pictures that I've had over the year that are kind of my Hall of Fame, Hall of Shame, corrosion stuff. Obviously, so we're in a turbine sump, so we don't have an electrolyte, but we do have condensation that can settle onto our copper pipe. This is just some great copper corrosion that you can see. We got probably ethanol vapors decomposing, creating acetic acid, causing a rapid corrosion response in some of these turbine sump areas. A slightly different style of copper corrosion, we get copper crystals that pop out of our mechanical line leak detectors. We get these nice buildup. There is a temptation to knock these crystals off, but this is a passive film that is developed over the copper. So the minute we knock these crystal coppers off, we restart the corrosion cell. So this is the copper trying to protect itself. Again, just great pictures, great crystal structure. Just some more kind of around the station corrosion stuff that I've noticed over the years. A comparison of a mechanical line leak detector that's been in a sump for a while versus a brand new one. Got massive surface corrosion, but we can see underneath the threads are still good. The rest of the mechanicals are still pretty decent. This bollard was at a coast, a site, and you can see that it is Swiss cheese. Makes for some really good reliefs though, but just kind of an interesting thing to show how aggressive even above ground corrosion can be. This is an internal monitorizer. We've got inside our riser all kinds of corrosion going on. We're about to see some better stuff, but the nice green. Older sites are obviously more susceptible to the stuff, but just really interesting corrosion patterns that I've witnessed over the years. Getting into a little more aggressive corrosion patterns, mechanical line leak detector corroding off the top. This is, I believe, the worst I've ever seen. One of the reasons why I included it. I've never seen the top of a leak detector actually begin to split away. It's pretty impressive. This is another monitorizer. You can see on the inside flaking beginning to occur. So the inside of the pipe is corroded so much that we're losing metal due to flakes. I believe this is that same pipe on the outside. Just a bunch of flaking going on. Really interesting stuff. More flaking on metal risers. You can see the whole structure on this, how much is peeled away. That was just sitting there and intact before the rest of it got knocked into this soup of water. But look at all that corrosion. How much of that integrity has been compromised due to just surface corrosion in a turbine sump? Pretty interesting. And the stainless still looks good. Again, it's the stainless develops that passive film. That's why stainless steel is stainless steel. It has a passive film that prevents it from corroding. But this is another angle of that same one, top down. Get more of a kind of a depth perception of that corrosion. And another monitorizer, more flaking. Just amazing, given enough time and a little bit of moisture, what corrosion can do to these monitorizer stands. One last Hall of Shame picture. Really interesting. I believe this is stainless steel, but it's corroding like it's copper. So I wasn't quite sure what was going on here, but I was just impressed by the braiding got totally obliterated by the corrosion. It's really, really unique. And this is just another kind of overall example of what the turbine sump environment looked like, and then a close-up of that. But one proposition too, maybe flood turbine enclosures and put a galvanic anode on the inside. You can't have an effective anode without electrolyte, but if you can flood it, you can have CP. So I don't know, maybe something to consider for the future. All right, thanks for watching.